Hey folks, in this discussion we're going to talk about particles circling in a magnetic field. We have briefly discussed that before. We're going to go into a little more detail. So we did talk about an example. So let's say you have a magnetic field pointing into the page. So that's our axis there. That means into the page. That's our magnetic field. And let's say we have a positive particle, and that positive particle at this moment has a velocity to the right. So if you do your Lorentz force rule, if you point your fingers to the right with the velocity, you curl them into the page with the magnetic field and stick your thumb out, your thumb will point up. So the force on this particle would be up, which is perpendicular to the velocity. So he's going to turn in a circle. So a few moments later, he'll be moving upward, but now the force on him will be to the left. Okay, so this particle's path will be a circle. Now, some information about the particle. Let's say that this particle is a 2.09 mega electron volt alpha particle. And let's say the magnetic field strength is 2 Tesla. Oh, sorry about that. 2 Tesla. Okay. We are going to calculate all kinds of stuff about the path of this little alpha particle. So the first thing we're going to calculate, the first thing I want to determine is what's the radius of that circle that that little particle is making. Now, in order to do that, we're going to set net force equal to ma. So net force equals ma. The force acting on the particle is the magnetic force, QV cross B. That equals m. He's moving in a circle, so that's A is v squared over r. One of the v's drops out, and we get the radius of the circle, okay, is mv over qb. Now, I've got the b, all right. I don't have any of the other 3 letters up there, right? I don't have m, v, or q. So let's start with q. What is an alpha particle? Well, an alpha particle is 2 neutrons and 2 protons. It's a helium nucleus with the 2 electrons stripped from it, okay? So the charge, and I'll write this over here, the charge of that alpha particle is 2 times the charge of a proton, which is 1.6 times 10 to the negative 19th coulombs. So your charge is 3.2 times 10 to the negative 19th coulombs. So that's Q. Okay, so we know the magnetic field. We now know Q. The mass. Protons and neutrons have roughly the same mass. So there's 4 particles, so you're going to take 4 times the mass of 1 neutron or 1 proton because they're the same. The mass of a proton and a neutron is approximately 1.67 times 10 to the negative 27th. So that's our mass in kilograms. Okay, so we got our mass. Well, finally, the velocity. What's the velocity of that little particle? Well, I told you that the particle is a 2.09 mega electron volt particle. What on earth does that mean? I'm giving you the kinetic energy of that particle. So we're going to use kinetic energy equals 1/2 mass velocity squared, or velocity equals the square root of 2 times the kinetic energy over the mass. Well, I've got the mass, the kinetic energy. That's your 2.09 mega electron volts. Okay. However, we don't know what that is. We need to have that in joules. So the kinetic energy, we start with the 2.09. Now a mega is 10 to the 6th. So that's how many electron volts of kinetic energy that little particle has. And we got to convert that to joules. Well, 1 electron volt is 1.6 times 10 to the negative 19th joules. So our kinetic energy in joules is, my calculator tells me 3.344 times 10 to the negative 13th joules. So that's my kinetic energy. So I'm going to plug that number in there and then this number in for mass, and that will give me the velocity of the particle. When I do that, I get almost exactly 1.0 times 10 to the 7th meters per second. Okay, so now in my radius equation, I finally have my velocity. So now I can plug and chug. Okay, so my radius will be, if I plug this in for mass, and I plug in this for velocity, and I plug in this for charge, and I know the magnetic field is 2. That was given in the problem. If I plug all that in, I get 0.104 meters or 10.4 centimeters. Okay, so that's the radius of the path that that little alpha particle is going to take. Okay, now another thing I want to calculate: what is the angular frequency? That's omega. Okay, well, you might recall that omega is defined as V over R. Okay, and it's V divided by the equation we got for radius was this. So mv over qb. Now you'll notice the velocities cancel out, and if I if I make this a non-complex fraction, if I simplify it, I get that. Okay, and we already have all 3 of those values. When I plug them in, I get 9.58 times 10 to the 7th. This would be radians per second. Okay, and then you can divide that by 2 pi to get revolutions per second. Okay, that's how many revolutions per second that little guy makes. Something very important to note there. Notice what's not in that final equation: velocity. Okay, so it turns out if I throw this particle into this magnetic field, no matter what, it's going to take him the same amount of time to take a lap. If I throw him fast, okay, and I'll kind of draw this here. If I throw him in there fast, so let's say here's our field. If he has a high speed, he'll have a fairly big radius. If he has a slower speed, he'll have a smaller radius. But the time to complete each of those circles will be exactly the same. The angular frequency will be exactly the same. This has a name. It's called the cyclotron frequency. Okay, so if you have if you're injecting particles into a magnetic field, they will always take the same amount of time to make their laps. It just depends on the charge, the mass, and the magnetic field. Similarly, we can find the period, how long it takes them to make one lap. So period, you might recall, there's 2 ways to do this. We can use 2 pi over omega, which is what I'm going to do. The other way to do this is you could use velocity is 2 pi radius over time and solve that for t. That would work just as well, but I'll use this top version. So we get 2 pi over that expression for omega, which is qb over m. And then if I simplify that, it's 2 pi mass over qb. Okay, and in this example, I have all those numbers. In this particular example, I get a period of 6.56 times 10 to the negative 8th seconds per cycle. So it takes the particle a very short time to make one lap in this thing. And that's called the cyclotron period. So there's some details about the motion of a particle in a magnetic field going in circles. And we also got to talk about what mega electron volts is. That's a unit of energy that's much smaller than a joule because you're talking about a single particle. So you don't use joules here. You use something called electron volts. All right, I hope that video was helpful, and thank you very much.